So spark up your Jupyter Notebook within the course materials folder using your Anaconda prompt if you haven't already. And let's dive into section 10. So we're going to start with deep learning classifier.ipynb and actually use TensorFlow to build a deep neural network that solves that same classification problem that we had before. So just like our other examples, we're going to use this fabricated data that represents whether a car should be traveling fast or slow given the distance to a bump in the road and how big that bump is. So the first thing we're going to do is just generate that data in exactly the same manner that we did before so we can compare the results on an even playing field. Let's take a look at the results of that fabricated data visually again just to make sure that it worked. And it did. Cool. So again, what we're showing here is a scale of 0 to 1 that represents the distance to a bump and how big the bump is. So if you're very close to a bump and it's very large, you're going to go slow, and that's what these yellow dots represent. If you're very far from a bump and it's very small, you can go fast, so purple represents fast here. And you can see we purposely have some overlap between these data points, but they tend to be clustered, somewhere in the corners. So let's see if we can construct a deep neural network that identifies those clusters pretty accurately. All right, so the first thing we're going to do is split our data into training and test data sets. We're just going to go straight into train test here to make sure we're evaluating things fairly. So we're going to take our entire feature data set and our entire label data set and split it up into a 20% test data set with 80% being reserved for training. We'll use a consistent random state so that you'll get the same results I do. All right, now to actually use TensorFlow and Keras, we just need to import the modules we need. So from TensorFlow, we'll import Keras because, again, Keras is part of TensorFlow now. Very nice. And from Keras itself, we'll import the sequential model, which will allow us to build up our deep neural network one layer at a time. And we'll import the dense layer, which is just a perceptron, a layer of hidden neurons. That's all we really need to work with. Go ahead and run that. And that should import everything we need and initialize it. All right, so let's start with a really simple neural network here. We're just going to start off with 2 layers and see just how easy that is to set up in Keras. So all we need to do is declare a sequential model. That means we're going to build up this model one layer at a time. We'll start with this initial dense layer that takes an input shape of the shape of our input data, whatever it might be. So I'm using the .shape command on our training feature data set to actually extract the number of dimensions in that data set automatically. That's just going to represent the x and y coordinates of each individual point as inputs into our neural network. And we will use the ReLU activation function because, as we said, that's often a good choice to start with. And that will feed into a hidden layer of 32 neurons in our network. We'll then have an output layer of one single network that has a final classification of fast or slow. And for a binary classification problem, we want to use the sigmoid activation function to actually convert the output of this neural network into a probability of being fast or slow. So let's go ahead and execute that. And we've set up our model. So we now have our graph set up within TensorFlow under the hood that we can just execute. Before we do that, though, we can ask Keras to give us back a summary just so we can double check that the topology is what we intended. So you can see we have here a dense layer with 32 neurons going into a single output neuron that provides our final classification, which is exactly what we want. Now we just need to compile that model. We'll specify the binary cross-entropy loss function because that's generally the right choice for a binary classification problem. For the optimizer, I'm leaning toward Atom these days because it tends to produce the best results overall. It tends to be a really good choice. And we will measure our results based on accuracy. All right, that's all there is to that. Now we can actually train our neural network. And again, that's just one line of code, so that's pretty cool. We're going to say model.fit, just like we would in scikit-learn here. Passing in our training features, our training labels. The batch size is just how many input points we want to process at a time. We'll let this run over 10 epochs, so 10 iterations of performing that gradient descent to try to iterate on the best weights and biases within our neural network. We'll set the verbosity level to 2 because that's what works best within a Jupyter notebook, and pass in our test data for validation. Let's go ahead and kick that off. And it just works. And it was actually pretty darn quick, huh? So there we have it, and you can see the accuracy as it does its training start to converge here. We started off with just 55% accuracy on our neural network's ability to actually predict the correct values from our training data, and it very quickly dropped down to around 84%. So that's pretty cool. But keep in mind that we're looking at the training accuracy while we're processing the training data. So to actually see if we're overfitting or not, we need to actually evaluate this on the test data set. We can do that very easily as well. We can just say model.evaluate, given our test features and our test labels, and print out the results from that evaluation. So it turns out our final accuracy metric here is 84.1%, and hey, that's about the best we've seen, right? I mean, we got similar results using SVC, we got similar results using logistic regression, and yeah, I mean, 84% is about as good as we can do in this data, and a neural network was able to achieve that same result. I think that's interesting because it does kind of point to deep neural networks as being this general purpose tool that really can do a great job on pretty much any machine learning problem that you might have. That's why Google uses it for everything. So instead of worrying about all these different machine learning techniques, you can focus all your efforts on this one, deep neural networks, and generally get good results out of it. However, maybe that was a little bit too easy of a problem for a neural network. So let's make things more interesting. And we'll actually have 4 different categories in our test data set instead of 2. And we'll make them all overlap in weird ways. And these can represent whatever you want. Maybe they're like different speeds, or so maybe instead of fast and slow, we have fast and really fast and kind of medium and slow, right? Whatever you want it to be. So I'm just going to append a couple of different clusters here to our test data here. I'm not going to go through the guts of how this code actually works. Basically, we're just going to call make blobs with 4 central points here and 4 clusters instead of 2, and the rest of the code is pretty much similar. We can visualize that as well. And here is our data set here that we're going to play with. So you can see that we now have 4 clusters in here, and they all overlap each other in strange, funny ways that are kind of hard to figure out. So let's see if our neural network can make sense out of that. Now, we are no longer in the world of binary classifications because now we have more than 2 categories. We have 4 categories. So now we have to do some extra pre-processing of our label data first. We have to one-hot encode our labels like we talked about in the slides, because at the end of the day, we just have individual neurons coming out of the top of our neural network that indicate probabilities for any given category. And for that to line up with our labels, we can't just use the number 3. We have to one-hot encode that so that we have 0s and 1s that are aligned with each one of those output neurons. And for a brief refresher, again, if we had our 4 categories labeled as 0, 1, 2, and 3, the 4th category would be category 3 because we started counting at 0, and we would one-hot encode that as 0, 0, 0, 1. If we wanted the 2nd category, that would be 0, 1, 0, 0, and so forth. Now, fortunately, Keras makes this really easy to do. It has a 2-categorical function that will just automatically take an array of labels and one-hot encode them for you. So let's run that really quickly and see how it works. So we printed out the 2nd label in our data set, label number 1 here, and the raw category of that is category 0. And after running 2-categorical on that entire set of labels, that's been transformed into this array of 1, 0, 0, 0, which is the one-hot encoded format for category number 0. All right, so now that our data is in the format that we need it to be in, we can split it up into train and test sets like we did before. So as before, we're going to set aside 20% for a test set and put everything else in the training data set, and we'll have a consistent random state again so we have reproducible results. And now we can build up our neural network again. So the main difference is that we now have 4 output neurons instead of 1, and each one of these 4 output neurons represents one of those one-hot encoding values. So whichever one of those 4 output neurons has the best value is going to represent our choice of classification. And to do that choice, we're going to use the softmax activation function. What that does is convert those outputs into probabilities, and then we can choose the highest probability as our choice of classification. So the initial layer looks just the same. We're taking the input shape of however many input dimensions we have using a ReLU activation function, and this time we're feeding it into a dense layer of 32 hidden neurons. And the output layer will be 4 neurons using the softmax activation function, so we can just choose the neuron with the highest value to pick our final categorization of one of those 4 outputs. Let's set that up and look at the summary. It does look as expected. We have our layer of 32 neurons feeding into an output of 4 neurons. Now we just need to compile it. And since this is no longer a binary classification problem, we'll use categorical cross-entropy instead of binary cross-entropy. Otherwise, it's the same. And now we can train it in the same manner as before. Batch size of 100, 10 epochs. Let it go and do its thing. Again, really quick, and it did converge pretty quickly as well, to about 73% internally. Let's evaluate the results again using the same manner as before. And we got to about 74% accuracy. Not bad considering how messy that data set was. I mean, those clusters were very loosely defined and they overlapped each other quite a bit. But let's see if we can make this model even deeper and add another layer of neurons to see if we can do a better job on this. And that will make this truly a deep learning case. So all we're going to do here is add another layer of neurons, another hidden layer here of 16 neurons. And you can see just how easy it is to do that in Keras. All we have to do is add another line here that says model.add dense16 activation ReLU. And now we have another hidden layer of 16 neurons in between our bottom layer of 32 that feeds into our output layer of 4. And it's a pretty common pattern to basically halve the number of neurons as you go up. So that's a good place to start from. So we went from 32, half of 32 is 16, and that will funnel then into a dense layer with 4 neurons at the output. You can imagine doing even another one with 8 neurons in there as well. So let's do that. The rest of the code is identical to before. The only thing we changed was adding that additional layer here of another dense layer of 16 neurons. So let's kick that off and see what happens. Ran really quickly, and turns out our final result actually was a lot better. So we're up to 81.4% accuracy now. So that additional layer in our deep neural network actually did do a lot of good there. That's pretty cool. So let's go ahead and take it even further. We've kind of found a direction here that's promising. Let's see how far we can take it. So yeah, let's go ahead and add that 8 neuron layer in there as well. So we're going to start with a layer of 32 neurons that feed that into 16, that then feed that into 8, that then go into our final classification of 4. So now we have a really deep neural network here, right? Let's kick it off. Still runs pretty quickly. And what did we get down to here? 82.5%. So now in previous runs that was actually worse than before, but you can see it's actually pretty close here. We're not actually getting a whole lot of benefit out of that extra layer. So that probably means we're just going to start overfitting things at this point, and that's not a good thing. So at this point, the network is probably more complex than it needs to be. We probably would have been fine just stopping with those 2 layers of 32 going to 16 and then going to our output layer of 4. We don't actually need that 8 layer one at all. So that's good. That's less processing we have to do, right? Now, another alternative to going deep is going wide. So what would happen if we just went back to 2 layers, but just added more neurons to that single hidden layer? So let's try getting rid of those hidden layers and just go to a 64 neuron layer at the input instead of 32 and compare those results. So again, we're going to width instead of depth here. And we ended up with 81.4% accuracy. That's pretty good still, right? I mean, comparable to what we had with our 2 hidden layers. And depending on the randomness and when you actually run this thing, it could be better or worse than the one that had 3 layers. So often you can get the same accuracy with a wide network as you do with a deep network. But the thing is, the deeper networks tend to converge more quickly. It also depends on the problem too. Like we talked about, deep networks can be good at identifying higher level features as you work your way up. But for a problem like this, where you're just trying to divide data into clusters, there isn't really a whole lot of depth to be dealt with, right? So it's not really the right kind of problem for a deep neural network necessarily. Now, if we allow this wide network to run over even more epochs than 10, maybe it would have done even better. And you can see it was still starting to converge quite a bit here. So I think there was some more benefits to be had by going beyond 10 epochs. Go ahead and try that, actually. So if you want a little bit of an exercise here, try running this wide network over 100 epochs instead of 10. Compare that to running the deeper network over 100 epochs and see which one converges faster. See which one gives you the best results at the end of the day. So really experimenting with deep learning is what it's all about. Just trying out these different topologies, these different approaches, and seeing what works and at what point you start to get diminishing returns. So that's really what a lot of it's all about, guys. So give that a shot, play around with these a little bit more, and we'll move on.